In this lesson, we're going to continue reviewing things that we need to know for grade 9 math. In particular, we're going to look at ratios, rates, percents, and decimals. Now, this is a fairly long lesson, so I'm going to start with one that's already filled in, just because I like to keep the lessons reasonably short, 15 to 20 minutes. And if I had to fill this one all in, it would definitely go longer. So we're going to start with a filled-in lesson for today. A ratio is a comparison of two quantities of the same type or units. So I'm just going to go through it, and I'll still probably jot some things down and highlight some things, but anyway, yeah, we'll use what's already here. So first thing I've highlighted is same type or units means, for example, I might compare goals to goals if I'm looking at sports, or dollars to dollars if I'm trying to compare two different objects that I want to buy, and so on. But the idea of having the same units means that if I compare them, then usually by comparing, it's the operation is sometimes going to be a division. In other words, we're gonna sometimes write it like a fraction, which is a division. Again, you'll see as we go through some examples. So, for example, the last time I taught this course, which is why this is already filled in, I happened to have 14 girls and 12 boys in the class. Therefore, the ratio of girls to boys was 14 to 12. Notice how I've highlighted girls in yellow and boys in green. And notice how the girls, the yellow, came before the boys. The 14 came first, the 12 came after. It's because of the fact that it's given as girls to boys. If the wording had been the opposite, if it said boys to girls, I would have put the 12 first and the 14 after. So order matters when I'm doing a ratio. And then we have there's two dots in the middle, they're called a colon, and that's how we often express ratios. Equivalent ratios are ones that are equal to each other. They're like equivalent fractions. So for an example of an equivalent fraction would be 1/2 is equal to 2/4. And I got the 2/4 just by multiplying the top and the bottom of the fraction by the same number. So I could multiply it by any number. If I multiply by 5, then I'd get 5/10, going back to the original fraction. Those are all equivalent, and they can all be reduced to 1/2. Likewise, with ratios, I can do the same thing. So for example, 2 to 3 is going to be the same as 4 to 6 if I just multiply both the numbers by 2. If I multiply both my original numbers by 3, I get 6 to 9. So we get equivalent ratios by multiplying or dividing each term within the ratio by the same number. So for example, 4 to 6 could become 8 to 12 if I multiply both the 4 and the 6 by 2. Or I could divide. 4 to 6 could become 2 to 3 if I divide the 4 and the 6 by 2. It's always possible to multiply. Doubling is the easiest one, but we can multiply by any number. It's not always possible to divide, at least not if I want to get non-decimal answers. So multiplying is the easy way to go. However, dividing lets me get things down to smaller ratios. And just like we want smaller fractions, fractions, 1/2 is considered a better way of writing a fraction than 2/4 or 5/10 because it's reduced to simplest terms. Same thing we want to do for ratios. We want to reduce them to the smallest possible numbers. So while dividing is not always possible and usually a bit harder to visualize, it's actually the better way to go. So state 3 equivalent ratios for each of the following. 4 to 7, so I could double each of the numbers, get 8 to 14, or I could multiply each by 3 and get 12 to 21, or multiply each by 5 and get 20 to 35. Notice how I can't divide the first one because 7 is a prime number. So nothing goes into 7 except 7 and 1, so I can't reduce it any further. 6 to 10, however, could be reduced. Both of those are even numbers, so I could divide them by 2 to get 3 to 5, or I could multiply them by 4, which I did in the next row, or double them, which I did in the third row, or multiply them by 10, which I did in the final row. That's an easy one because all I have to do is add a 0 to each end. But it's also, it's the easiest way to just add a 0 to 6 and 10 to get 60 and 100. It's also the least useful to have these big numbers. And likewise, 15 to 25, that can be reduced. If I divide the first and the second number by 5, I get 3/5. That's in the simplest form. And then you can see a bunch of other ones that were gotten by multiplying. Except for this one here, which is an interesting one, I think, because in order to really see what that 6 to 10 one is, it is equivalent, but first you'd have to reduce it to 3 to 5 by dividing by 5, but then you'd have to double the 3 to 5, and then you'd get 6 to 10. So that one is kind of interesting. But they're equivalent. A unit rate is a quantity associated with a single unit of another quantity. So now we're not talking about things that have the same units. So for example, dollars per hour. Those are two different units. Kilometers per hour, dollars per case, goals per game, grams per serving, dollars per liter. Every one of these, we're comparing two different units. Notice how when the units for dollars comes before the number. That's just how we write dollars in English. And so it always comes first. For every other one, like kilometers per hour or goals per game, grams per serving, the units come after the number. And then that slash that you see there, right, that we used to read as per. Now, it means divide, just like it always, you should know that means divide from before now, and it still means divide, but we read it as per, dollars per hour, so on. A rate compares one quantity in one unit to a quantity in another type of unit. A unit rate, however, helps compare, basically what it does is it reduces things to a single unit of the one we're dividing by. So in other words, $10 per hour could be thought of as a unit rate for hours. So maybe that's what someone's getting paid. So the unit rate, so that how much do they get paid for 1 hour? They get paid $10 for every 1 hour they work, or 65 kilometers for every 1 hour they drive, or $2.99 for every one case someone buys. So a unit rate means how much, so that number involved with a unit rate lets us know how much of the first unit goes with one of the second unit. So determine the unit rate in each case. If someone happens to score 72 points over 18 games, then we can divide 72 by 18 and we get 4 points per game. And notice how the units work themselves out. 4 points divided by 72 points divided by 18 games reduces to 4, and it's points per game. $4 basically, or $3.99 divided by 5 kilograms gives us 0.08 per kilogram. Patrick looks at flyers for two different grocery stores and finds the following. Store A has a 12 case for $1.99, so we can get the unit rate for that. So for store A, it turns out if I divide $1.99 by 12 bottles, in that case, that it costs 17 cents per bottle. Store B gives you an 18 case, but for $3.50. If I divide the $3.50 by 18 bottles, it turns out that it's 19 cents per bottle. So, obviously 17 cents per bottle is cheaper than 19 cents per bottle, so we will go with store A. Percents, decimal, and rounding, another set of skills that you need to be good at. What does percent mean? It means out of 100. Per means out of, and cent comes from a Latin root for 100. Those of you who like history might know that the Roman soldiers were called centurions. That's because they fought in groups of 100. So it's the same root. Percents, fractions, and decimals are all connected through the operations of multiply and divide. So to change from one type of unit to another type of unit, we need to multiply or divide. So it's not about adding or subtracting. So to make something into a percent, we need to get it to a decimal form first, and then we multiply it by 100. And an easy way to multiply a decimal by 100 is just to move the decimal place 2 places to the right. So, for example, if I had 0.13, as you can see on the right, if I move the decimal place 2 places to the right, then that becomes 13, and then I write the percent, it's 13%. To get rid of a percent, we just do the opposite. We divide by 100, and we move, that's the same as moving the decimal 2 places to the left. So if there's no decimal written, like here at 73%, I can always assume there's one at the end, and if I move it 2 places to the left, that becomes 0, and we can put the 0 in front, 0.73. So, complete the table. So if we start with a fraction, 3 over 100, then if I start with this, I can change any fraction to a decimal just by dividing, right? A fraction is really just a division that hasn't been done. So 3 over 100, I could put 3 divided by 100 in my calculator, and I get 0.03. And then if I want to change it to percent, I would move the decimal 2 places to the right. I don't need those zeros up front anymore, and that's just 3%. If I start with 0.25, then I can again change that to a percent easily by moving the decimal 2 to the right, and that's 25%. But to change it to a fraction, I need to understand how decimal places work. Well, no, actually, well, I do, but actually, for now, I'm going to save that for a second. For now, let's just worry about the percent. We'll change. Actually, what we'll do is we'll take the percent and make that into a fraction. So if I have 25%, we already know that means 25 out of 100. So then I can take that and write it as a fraction, 25 over 100. Don't need the percent sign anymore, but I do need to reduce because that's not in lowest terms, and fractions always need to be in lowest terms. So 25 over 100, you might recognize that 25 goes into 100 4 times, so you could reduce the top and the bottom by 25. Or you could just, if you didn't recognize that, you might just think, okay, well, I can divide top and bottom by 5, and that's what would give me the middle number of 5 over 20, but you should always check to see if you can go farther. And in this case, you definitely could go farther. It keeps going down to 1 over 4. Again, if I was to take 115%, again, that means out of 100, so I could start with that, and then I could reduce it. So I could reduce it as a mixed fraction if I wanted to, as 1 and 15 over 100, but I still need to reduce that 15 over 100 to 3 over 20. 5 goes into the top and bottom, or as an improper fraction. So 115 over 100 could be I could divide the top and bottom of 115 over 100 by 5, and I get 23 over 20. We're going to talk about mixed and improper fractions in a separate lesson, so don't worry if you've forgotten about them. We're going to review that. So here's rules for changing things from one form to another. As I already said, if I want to go from a fraction to a decimal, just divide it out. If I want to change from a fraction to a decimal, this one is a little bit, this is where we need to know some rules. So say I had, I'm just going to write this out here. Say I just had something like, 5.71921, I don't know, just make up a number. You know there's places, right? You've learned about places. So this is the ones place to the left of the decimal. And if I had a number out front here, this would be the tens, and this would be the hundreds, and so on. So you know about places. So let's just remember them for a second. The first one to the right of the decimal is called the tenths. I'm going to actually write that as a number. It'll be easier. So that's tenths place. And then the next one is the hundredths place. And the next one is the thousandths place. We just keep adding zeros into it, but it's 1,000th. Then the next one would be the 10,000ths. And then the last one would be the 100,000ths. And it's not really the last one, it's just the last one that I drew. There could be a millionth place after that, and a 10 millionth place, and so on. What matters, though, is that if I want to change something from a decimal to a fraction, look at where the last decimal number is. So in this one right here, 5.71921, I could easily write that as a fraction by recognizing that my last number is in the 100,000ths place, And so then I could write the number again without the decimal, so just 571921, and put it over 100,000. Once again, that's because the last number was in the 100,000th place. And so that always works. And of course, I've reduced if I can. This one doesn't, I don't think that one's going to reduce. You can see I've got another example from when I wrote this out previously, 3.147. The 7 is in the thousandths place, and that's the last number, last decimal, last digit. So I put it over 1,000 without the decimal. So that will always work. Just remember to always reduce. From a decimal to a percent, what we want to do is we want to move the decimal 2 places to the right. We already talked about that. And if I want to go from a percent to a decimal, move the decimal 2 places to the left. That's like multiplying by 100 or dividing by 100. A fraction to a percent, we don't usually have an exact way to do this. Usually what I do is change it to a decimal, then move the decimal 2 places to the right. One other way I could do it is I could, if it's easy to change the fraction to an equivalent fraction out of 100, that would be fine as well. So for example, and this only works in certain situations, but say I had something like 3/10, and I wanted to change that to a percent. I could change it to an equivalent fraction out of 100. I just multiply the top and the bottom by 10. And then that would be, as a percent, I would know that's 30%, because if I got 100 on the bottom, then it's a percent. So if it's easy to change it to a fraction out of 100, then that was another way to do it. Percent to a fraction, put it over 100, then reduce, and we already did that in the table above. Example 2, find 35% of 425. So this is yet another thing you need to know. You need to know how to find a percent of something. So first thing you need to know is that of means times when we're doing math. So it means multiply. Okay? And whenever we're working with a percent, we have to change it to a decimal before we multiply. So I change 35% to 0.35. I change of to times. Brackets there just indicate that we're multiplying, and I do 0.35 times 425. In the calculator, which I've already done this, so you just have to trust me that it worked out. 0.35 times 425 is 148.75. Easy peasy, hopefully. Example 3 is a little different. It says 8% of what number is 22. So it's not saying take 8% of 22. It's taking 8% of some unknown number, and the answer is going to be 22. Well, if that's the case, I'm really doing the opposite. So the opposite of doing 0.35, for example, of 425, of doing 0.35 times 425 would be to divide by 0.35. So in other words, change your percent to a decimal and divide by that decimal. So I could check my work, but I know I'm talking about example 2 now. I don't mean to confuse anybody. I just thought that this would be a good thing to check. So I could check this work by doing the opposite. So if I took my number of 148.75 and divide that by 0.35, I should get the number I started with. 148.75 is 35% of 425. So doing the opposite, dividing, should get me back to where I started. Let me just do that. 1.4, I've already forgotten what the number was, 148.75 divided by 0.35. This is a funny calculator. My calculations are on the left, bottom left, and my answer, as you can see from the little notes there, show up on the right side. So my answer is on the right. It says 425. So I got back to what I started with. So yeah, opposite is what does it for me. So if I want to find the opposite, if 22 was my answer, and I want to find out what number I started with, then I would do 22 divided by 8% as a decimal. 8% is 0.08. Don't forget this 0 between the decimal and the 8. Because if I move my decimal place 2 to the right, that implies I have to stick a 0 there so that I can do it. If I don't put the 0 there, then that'd be 80%, and that's a much bigger percentage than 8%. Anyway, 22 divided by 0.08 is 275. And this over here on the left must be just something from a discussion we had in the past. I don't think I need to decipher it now for our purposes. Let's just stick with the one way that I did it. All right, so that's good. Last example. A coat is on sale for 30% off. Its regular price is $58. What's the sale price? There's two ways of doing it. One way is I could find the discount, find out how much money is being taken off. So I could find 30% of 58. So 0.3 times 58, that gets me $17.40. So the sale price would be the $58 minus the $17.40 minus the discount, and I'd get $40.60. Or, and this is actually, the second way is actually the way I prefer to do it, if there's 30% off, that means that the sale price is going to be that there's 70% left. In other words, if the original coat cost 100% of its value, and we take away 30%, it's on sale, then now we are left paying 70%. So things always add up to 100%, of course. So I could go directly to my answer by doing 70% of 58, which is 0.7 times 58, which also gives me $40.60. These are the same, aren't they? They should be the same. They're just two different ways of doing it. If tax is 13%, what's the final cost of the coat? The final cost is going to be 13%. Well, again, there's two different ways of doing it. So I could just find the tax, 13% of $40.60. So 0.13 times 40.60 is $5.28. And then again, now I'd have to add that to the cost. So $5.28 added to the 40.60 gives me $45.88. Or I could add 13% to the cost. So 13% to the cost means if I take 100% and add the 13% tax, 100% of is the cost of the coat, add 13% tax, that means I'm going to have to pay 113% of the cost of the coat when I've got the tax added on. Then I could change 113% to a decimal, which you can see there is 1.13. And we multiply that times $40.60, and again we get $45.88. And again, those are the same. What do we have here? Looks like we have a little bit more. Sorry, I forgot that we have rounding on this one as well. So quickly, rounding. Rounding means reducing the digits in a number while trying to keep its value similar. So we got this place value chart. So I've highlighted the decimal in green, and again I've shown you the different things. To the left we've got the tenths, hundredths, thousandths, 10,000ths, and so on. To the right we've got ones, tens, hundreds, thousands, and so on. When we're rounding, find the place value asked, and then look at the number on the right. And if the number on the right is 5 or more, then we round what we're looking at up by 1. And if the number to the right is less than 5, then the number that we're looking at stays the same. So if we want to round to the nearest hundredth, then I've highlighted the hundredths spot in yellow. That's the 4. So I look to the right of the 4, and that's the 6. 6 is a number that's greater than 5, so I'm going to round up to 5 here. So in the hundredth spot, I round up from 4 to 5. In example 6, I would round to the nearest tens, not tenths, but tens. So that's the second place to the left of the decimal. So that's what I've highlighted in the 5 there. Or the 5 I've highlighted in yellow. But that means I look to the right of that again, into the ones column. That's 8. So that's a number bigger than 5. So again, I'm going to round my tens column up by 1. And so I round that up to a 6. If I'm rounding numbers that are whole numbers, though, anything to the left of the decimal, if I'm rounding anything to the left of the decimal, I need to add zeros for all the places between where I round and 0. So in other words, notice how if I round to the nearest 10, I have to add that 0 in the ones place. Because if I leave that 0 out, it would just say 366, which would not make any sense to round 3,658 to 366. So always think about your answer and make sure it makes sense. Rounding to a nearest nickel is slightly different, because for rounding to the nearest nickel, that's at 5 cents, right? It's like skip counting by fives, 5, 10, 15, 20, and so on. So we have to round it so that it either ends with a 0 or with a 5, and whichever one it's closer to. So we look at the last number. Well, if it's dollars and cents, as it is in here, we look at the nearest penny. So 3, 4, or 5 is going to round up to a 5, and 0, 1, or 2 is going to round down to a 0. But this is a 3, it's going to round up to a 5. Finally, on this review, this big long review, we got measuring. We're talking about measuring a bit. This is a what's it called? Imperial. You're used to metric, so am I. But there is another measurement system called imperial. That's the one with feet and inches and miles and so on. This is a picture, or a few pictures of a ruler that's in inches. And the funny thing about these rulers is they divide things up not into tens like metric does. That's what makes metric so great, is it divides things into tens. But if we look at, just to pick any 1 inch here, so let's look at this one here, between the 2 and the 3. Notice how there's different length lines. I've zoomed out as much as I can. So exactly halfway between the 2 and the 3 would be 1/2. Exactly halfway between the 2 and the 1/2 would be 1/4. Exactly halfway between the 1/2 and the 3 would be 3/4. Then I can divide each one of these in half again. So say I go between the 1/4 and the 1/2. Well, let's go between 1/4 and 2. So this one here. Well, I just keep cutting them in half. What's half of a quarter? Well, when I cut a fraction in half, one way to do it is just make the denominator twice as big. So half of a quarter is 1/8. And then in between each of these is going to be different things. So this would be 3/8, and this one's going to be 5/8. And as you can see, there's lines in between that. There's 16ths, and it's really going to be hard for me to write these ones. This is a 16th here, this line here, because if I double the 8, then I get 16 on the bottom. And you can see there's even a shorter line, a really teeny tiny line there. That's going to be a 32nd. So it actually divides down into 30 seconds. So the way we read the ruler, we're supposed to be going, for this one, we're supposed to be going to the end of the green line. So there's this green line that chops off right here, right? So we take the whole number, so whatever the whole number is, that's 4. And then we read the next thing after it. So that line there is 1/8. Again, here's a half. Half of that is a quarter. Half of that again is 1/8. So it's 4 1/8. The green line for this one stops after the 9. And it's past the 1/2. So it's beyond that. But it's not at the 3/4. So it's halfway between a half and 3/4. So it's going to be 1/8, and that would be 5/8. If you count them up, the lines up 1, 2, 3, 4, 5, so the spaces of that same thing, then it would be 5/8. The next one goes past the 4, and it goes to one of those second shortest lines, which are 16ths, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of the 16ths, as you can see. The last one goes past the 6, and it goes to the very smallest line there, this very short line here, so I have to count the smallest ones. 1, 2, 3, 4, 5, 6, 7, 8, 9 of those 30 seconds. So that's how you can read a ruler, just for, it's going to come up in some of our questions where we have to work with imperial. So there's a whole bunch of review in this lesson. I went through it pretty quick. You might need to go back over some of it and just slow it down. That's a great thing about a video, is you can rewind it, so to speak. I know it's not really rewound, but go back over it and replay it as much as you need. And pause it, think about it. All right, good luck.